Hello everyone, my name's Mark Harmon. I'm a research scientist and engineer at Facebook in London, and this is the work of the whole London probability team who've been working on deploying metamorphic testing at scale at Facebook on our dub simulation system. So in this talk I'm going to tell you a little bit about the dub simulation system, enough context to understand how we do metamorphic testing and regression testing, and that's implemented in a system we call MIA, the Metamorphic Interaction Automaton. And this allows us, in combination with an offline mode deployment, to tackle problems of flakiness and scalability, as we'll see. So dub is a simulation that runs on the Facebook infrastructure. So the Facebook data stores and processing elements make up the infrastructure, and on that infrastructure we deploy bots. The actions performed by those bots and the observations that the bots can make are made through the real Facebook infrastructure in exactly the same way that normal users use the infrastructure. So if a bot were to send a message to another bot, it would use exactly the same stack of tech that you would use if you were to send a message to a friend. So the reason we do this is because we want to tackle harmful behavior, the potential for users to potentially do harmful behavior on the platform, to misuse the platform in ways that it wasn't intended for. So we reward these bots for behaving badly, essentially, on the platform. I should point out that all interactions in dub are between dub bots, and they are isolated from production completely. We described how we do that in a separate paper. This paper, indeed, which describes the web-enabled simulation approach that we use at Facebook to do simulation. So I'd refer you to this paper for details about the dub system itself and how we do web-enabled simulation. In this talk, I just want to mention enough about that so that we can explain how we do metamorphic testing. So suppose we're trying to deal with harmful behaviors like scamming and spamming. These are kind of behaviors that involve crawling. So our bots are going to crawl around the platform and are going to try and find potential other bots that they could treat as victims. So we use an approach called mechanism design to search the space of product improvements that can tackle these behaviors, and we're more concerned with moving from detection over to prevention in exactly the same way that in traffic systems prevention is actually stopping people from speeding with a speed hump, whereas detection is only really catching them at speeding. In the UK, we paint our cameras, our speeding cameras, yellow so that we can try and make it into a kind of a prevention technology. So we have lots of systems at Facebook for detecting behaviours and jumping on them when they happen, but what we want to do is be able to prevent them from even happening in the first place. So we reward our bots for crawling, and the actions and observations they perform on that infrastructure, we can apply limits to those. We can apply rate limits that affect how the bots interact with the real infrastructure at this mechanism layer. The reason for that is because we can't recompile the entire back-end infrastructure for every possible product change we might experiment with. So instead, we want this mechanism layer approach, which allows us to essentially simulate all sorts of product changes in parallel at once very fast. It's a kind of fast genetic improvement, if you will, and we talk about this in the paper. So the oracle problem is the problem that if you knew what the output should be for an input, then you wouldn't really need to be testing because you'd have an automated approach to know what the correct output should be. So you could write a formal specification to know what the output would be, but that's expensive and slow, and things move fast at Facebook. You could use a model as a reference. That's a useful solution, but once again, if the system itself is changing very fast, it's hard for the model to keep up. You could use an implicit oracle. So for example, in our crawling behavior, we use this. We say, well, it shouldn't crash. And that's kind of okay, but it's a very basic testing requirement. It's not really testing whether the simulation is doing the right thing, it's just testing that it's not broken. You could use another system as a reference, a kind of n-version computing, or you could maybe use the same system as a reference for itself, and this is metamorphic testing. Essentially the idea is you do two runs. So imagine we're doing two bot traversals on the platform, crawling here, starting from the same input state and the same initial input. So we've got a starting state S0, we've got an input I, and we run two runs of our bots. And you might think, well, if we start in exactly the same state, they'd do the same thing, but of course they won't, because they're running on a platform that's changing and it's highly non-deterministic, and therefore they'll diverge pretty soon. So what we really want is an offline mode where we pre-capture a whole lot of data, and now we're not really running on the real social graph, but we're running on a kind of cached snapshot of a piece of that social graph. We take a strongly connected component. Now if we run a harmful bot and a harmless bot in offline mode in the same starting state, but we now rate limit them. So they're only allowed to, in this crawl, they're only allowed to look at most one other friend. Now what happens is both bots do exactly the same thing. This is giving us a metamorphic relation between the two bot behaviors. So we say that if we start a harmful bot and a harmless bot in the same state with the same rate limit, and that rate limit is maximally constrained to be only one visible user at any given time, these bots must perform the same trajectory. This is because we're in offline mode, so there's no kind of non-determinism, and because although the bots are using different machine learning algorithms to determine their behavior, the rate limit means that they're constrained essentially to only have one choice open to them. So this is an example of a metamorphic relation. In the paper, we show how, in section 3, metamorphic relations can be considerably generalized. So instead of thinking of it just as a pairwise relation, we can show that actually it's very easy to define metamorphic relations for an arbitrary number of runs, including one. And when we have one run, then this becomes essentially end-to-end testing. When we have two runs and one of them is on the old version of the system, we get regression testing. So we've implemented regression testing, end-to-end testing, and full metamorphic testing for arbitrary numbers of runs in our MIA system at Facebook. And the paper describes how this is a nice general theoretical framework, but also that corresponds to a nice simplified general implementation infrastructure for us at Facebook, which is great. So traditional metamorphic testing is n equals 2, but we have plenty of metamorphic relations that have higher cardinality. So here's one where there are 3. There's a kind of transitivity property. Suppose I have 3 rate limits, A, B and C, and they're such that they get more permissive as we go up the scale. So now if we look at the trajectories for A and C, and we get a particular trajectory, there may be a prefix that they agree on. It might be empty, but let's suppose it's non-empty. Then what happens with the interposing rate limit that's less permissive than C, but more permissive than A? So it allows the bot to do more things. Because it's deterministic, and because we're only changing the rate limit and we're starting in the same state, what we find is that the bot with rate limit B must respect the shared prefix of the bots with A and C. So what typically happens, of course, is we get this behavior, but the only thing we can test for is that the intersection is preserved. What we typically will see is that the prefixes actually follow the same structure as the subsetting structure of the rate limits. But it could be the trivial one where they're all the same prefix, but in general it tends that the more permissive one has a longer prefix with the less permissive ones, and so on. So you can imagine we could generalize this to an arbitrary sequence of rate limits and thereby get arbitrary arity metamorphic relations. Another thing we do is statistical metamorphic testing. So suppose we start off in the same state, but we have a bot whose persona is to be a 20-year-old or 20-something, and another bot, a 50-something, perhaps a bit more like your speaker today. Now, 50-somethings tend to visit different kinds of things on a social network than 20-somethings. So we might expect that if we look at the average age of users visited in a session on Facebook by a 20-something, then that would be different to the average age of people visited by a 50-something. And that's true in the real platform, and of course we expect it to be true in our simulations. So now we're capturing a statistical property that the ages visited by bots with personas in their 20s should be less in general than those of bots in their 50s. And that's a statistical property. It's not always true, so we have to have enough sample size for this metamorphic relation to hold. So in the paper we give lots of results about the execution of our metamorphic relations, and in particular I want to draw your attention to the fact that we tackle the flaky test problem. So in online mode we do experience flaky tests, as you can see from these results in that flaky column there. But in offline mode we have managed to really drive down the flakiness. And in the results we reported over 3 days of execution time of this system at Facebook, we actually found no flaky tests in offline mode. So the combination of offline mode and metamorphic relations allows us to really tackle some of the challenging problems of testing. So one of those is the oracle problem. For simulations, it's not only a hard problem, but it's actually the hardest you can get, because not only is the oracle not known, it's inherently unknowable. We talked about our metamorphic testing system, the Metamorphic Interaction Automaton, MIA, and briefly mentioned how we use mechanism design as a kind of fast genetic improvement. That's covered in the papers. And we talked about flakiness and regression testing. Looking forward to getting your questions, and thank you very much for listening to the talk.
All right, so I guess we're live. Welcome everybody to this track about some big companies' practices, cases at Facebook, Google, and IBM. This is software engineering practice paper. And we have one of the authors, Mark Harman, very known in the software engineering domain. And we are here to answer your questions. Since there are no questions on the chat, I can start with my own question. My question is a recurring question, actually. So you wrote a paper and you provided some evidence about the flakiness of the test that has been reduced, but you used only the Facebook domain. So the general question is, what do you think that in your paper does not apply in other domains, like Google, like Android apps, if it was not on Android apps, or so how your result would relate to other domains than Facebook?
Thanks. Yeah, that's a good question. Yeah, I think that's probably one of the big differences between the SEEP track and the general track. You know, what you gain is the fact that it's evaluated on a real industrial system, but what you lose is the comparison with all sorts of other systems. So the honest scientific answer to your question is I just don't know.
Okay.
The speculative answer is that I think that the idea of pre-caching web results so that you have a kind of offline mode is definitely going to be a very good way of tackling flakiness. I think it's wrong. We talk about flaky tests as if the tests are the thing that's at fault, but actually it's just the system, isn't it? It's the system we're testing is non-deterministic.
Mm-hmm.
So what we found was, yes, for sure, if you're testing a web-enabled system, then it's going to be highly non-deterministic. And in our case, we're testing a simulation, so there's extra sources of stochastic behavior there. But we were able to, and because we're testing a web-enabled system that is actually based on a social graph that's changing all the time under your feet, you know, that you could have these bot traversals where it would change just because somebody changed their friends halfway through the traversal and the bot goes a different way. But by doing this pre-caching, that was very effective. And I think many organizations like Google, Amazon, and so on would be able to pre-cache a large enough part of the overall back-end infrastructure in the same way that we do. So speculatively, I'd say that idea applies, and it's a good way of tackling flakiness. But scientifically, I just can't say.
Okay. So let's see what Tim is saying. So Tim says, I wonder about the name metamorphic testing. If you could call it anything else, what might that be? Magic or loosely goosey expectation, inspection, or something else?
I like loosey goosey. Yeah, that sounds pretty good. But I think if we'd called it that, people wouldn't take us seriously, Tim. Actually, nobody takes us seriously anyway, do they? So that's not a problem. I quite like metamorphic. It's got a kind of, it sounds very clever. That's nice, you know. I mean, but you're right in a way, I suppose. I mean, I think it's a kind of relational technique, isn't it? You know, I mean, that's what's special. Well, in the paper we showed, there is a little bit of science in the paper. It's not all just like, here's our groovy results from Facebook. I think the interesting thing is, metamorphic testing is the most general kind of testing in a way, because you have multiple runs and then you have a relation over those multiple runs. And what we show in the paper is therefore regression testing is just a special case. You have two runs and you have a relation on them, which is always equality in some sense, right? Metamorphic in general, you could have, as we show in the paper, you could have three runs and we have a kind of subsetting relation between them and so on. And then traditional testing, end-to-end testing, or it's just you have just one run. So really metamorphic testing is testing in its most general sense. I have multiple runs and I have some relation that holds between them. And people often talk about it, it's a way of tackling the oracle problem and so on, but it's really just a way of saying, okay, if I have an abstraction, if I have my relation and it's over multiple runs, I've just got more chance of doing more with a partial oracle than if I only have the one run. And that's what I think is the really deep insight. Some of my colleagues at Facebook say to me, well, this metamorphic testing doesn't seem that special. You just do multiple runs and compare the results. But I mean, practically, that's just a natural practical thing to do. But scientifically, I think it's really interesting that it sort of subsumes all the other kinds of testing.
Okay, Tim answering, but I get up on the oracle used to define the relation. Aren't there bad relations? Uninformative relations?
Yeah, I guess like in any test vacuous things, like we could test that. We could have a relation lambda xy dot true, right, which takes your two runs and just always says pass the test, right? So that would be very uninformative, right? I didn't quite understand the point you made, Tim, but I get up on the oracle used to define the relation. Perhaps you'd like to. I think that there's a typo, or I don't understand it. Yeah.
Yeah, neither do I. Anyway, Mark, what would be now the next steps? Or let's take this question from Sergio. How difficult was it to come up with the metamorphic relations? And do you prioritize them somehow?
Oh, I didn't see that one in the chat. Anyway, great. So what was the question again? How difficult was it to define the metamorphic relations? Yeah, that's a really good question.
If you prioritize them somehow.
That's an interesting question. Yeah, what the thing about the metamorphic relations was, it's a bit like this. Like once you think of one, you think of loads, but it's hard to think of the first one. So once we realized that, hey, this interplay between the constraints that we put, so we're actually simulating this problem where you have these kind of rate limiting constraints that say, oh, they can only send this many messages, they can only do that many of this thing, they have to do this within that time. Once you're making this counterfactual world where you have those constraints, and then you have this concept that the bots essentially have a trajectory. Now you suddenly realize, oh, once I think about one of those, I got lots. So we realize, oh, if we constrain it really tightly, then that constrains what they can do. And now they can't do very much. And that leads you to a whole load of decisions. And then we do, but what if we constrain it some other way? And then we think about the trajectories and prefixes and all the natural things you do with sequences. So I think the key is you have to think like, what are the key properties of the thing you're trying to test, and then what types are they, and then naturally metamorphic relations spring up. If they're sets, then you think of set-based ones. We've recently moved to a set-based model for events, and we think of all sorts of relations like that. But it's a good question, because I think that is the big challenge with metamorphic relations. And as we say in the paper, that one of the really important scientific avenues that I think the research community should be addressing, and is addressing, but needs to address more, is how do we automatically discover metamorphic relations? I think it is a very powerful way of testing. And we found, by the way, incidentally, that a lot of times the metamorphic test would pass, but would reveal problems because the individual runs would fail, because by definition, we're testing these kind of special constraints, like when this thing's very constrained, or that thing's very permissive, or this thing's in a... So they're kind of corner cases, a bit sort of baked into your metamorphic relations. And oftentimes, even if the metamorphic relation would hold, the individual test, the individual run would throw up an error. And that was quite interesting.
Okay, we have 2 additional questions and only 2 minutes remaining. So Puyan is asking, would you please elaborate on minimal mechanism equivalence and interaction faults? Interaction faults are extremely difficult to capture in high-dimensional spaces where we have many features. Do you need assumptions regarding the degree of interactions?
Yeah, that's a great question. I think there's a lot of exciting research to be done that would bring together combinatorial interaction testing and metamorphic testing, because essentially, there feels like there ought to be an intellectual connection there. And certainly we found that by having these 3 moving parts, so we had the behavior of the bots, so we have various different ML algorithms for training bots to behave in different ways. Then we have the constraints that we get with the mechanism, and then we have the underlying, what the simulation's doing, the sequences it's producing. And the interaction between those 3 was where we would get the most interesting metamorphic relations. But we didn't have a concept of, have we covered all the possible interactions between them? So it'd be really nice to have a kind of blended combinatorial interaction metamorphic testing approach, where you could say, I've now got pairwise metamorphic relation coverage, or something like that. And it would throw up, probably would help answer that earlier question, like, is it easy to define metamorphic relations? Because your combinatorial metamorphic relation system would throw up these gaps that you hadn't thought of. And then you'd think, okay, what can I ask that connects this one from this choice, this rate limit with this trajectory question with this kind of something like that,
Okay,
yeah.
Mark. Now a yes and no answer. So Sigrid is asking, if I understand you right, utilize the constraints as the metamorphic relation? Yes or no?
Yes.
Okay. So we have now only 8 seconds. We say thank you to Mark. A pop-up will show up now on the bottom right. And if you click, then you can continue.